Welcome to this presentation on building 3D virtual worlds for monocular images of urban road traffic scenes. In this work, we propose a four-step pipeline to build three-dimensional worlds from monocular images that can be edited and animated to create interactive content. 3D modeling is an integral part of many graphics applications. Automated processes for 3D reconstruction typically output either sparse point clouds, blob-like models, or textured billboards, and lack the required detail and finesse. As such, modeling realistic scenes is still largely a manual process. Sophisticated modeling tools like Blender, 3D modeling of environments requires significant manual effort into placing objects at the right position. This video, sped up to 50x, is indicative of the time-consuming effort required to set up basic scenes. We propose a pipeline to automate the modeling process given a monocular image to approximately replicate the scene with selected objects in 3D, which can further be edited. Novel contributions are captured in an automated workflow that uses deep learning for depth estimation, perspective correction, and a rendering engine to construct a 3D environment from a monocular image. Our workflow, if integrated into a modeling software, could be used to significantly speed up the process of modeling urban environments by eliminating the need for human in the loop. These worlds can be rendered as is and animated to create vibrant content. Given an input monocular image, use a convolutional neural network to generate a dense depth map. Our model of choice here is one proposed by Goddard and colleagues. The per-pixel depth is averaged within a semantic segment to obtain per-object depth, followed by some corrections to ensure that the relative depths of objects are maintained in the 3D world. We then use direct linear transform by selecting a few points in the image to obtain a projection matrix that we then use to obtain the orthographic positions of our objects of interest as they would appear in the real world. As such, we obtain 3D positions from steps 1 and 2 as well as the semantic label of an object. We pass these on to load a 3D model from a curated database of models into the virtual world at the computed positions, perform an AABB collision detection to ensure that models do not intersect, and render the same. This virtual world can then be edited with the addition and deletion of models as well as animated to create a living virtual world. First user study, we generated a video of fly-through of two virtual worlds that starts from the point of capture of the scene and moves forward into the scene before providing an aerial view. The user is made to view this video along with 4 potential RGB images from which the video could have been generated, with the task to identify the correct source image. Out of the 41 participants, 37 respondents got both answers correct, 2 got one correct, and 2 got both wrong. For the 2 respondents who got one correct answer, they both got the answers correct for the second image. We observed that the question on the first image was perceptually more difficult than on the second, which is validated by a relatively higher structural similarity index, where the options for the first image are structurally more similar to the source. In our second user study, we provided the user with the source RGB image and its corresponding 3D virtual world and asked them to rate the image-to-image similarity on a 5-point Likert scale. Images S1, S2, S3, and S4 were rated an average of 4.17, 4.24, 4.0, and 3.49 respectively. We computed a Chromebox alpha, which is indicative of whether a design test accurately measures the variable of interest, of 0.803, which is a good goal. Given an input image, our four-step pipeline first creates a virtual world, which can then be edited to add and delete models, animate them to create interactive virtual world.